Welcome to the third lesson in topic 9, which is about stoichiometry. In this one, we're going to talk about limiting reactants, but I also want to introduce one other concept to you, and that is percent yield. So let's get started. With percent yield, this is a calculation that's made that if you theoretically come up with, if I do this reaction, theoretically I should produce, if I have this much reactant, I should get this much product. It's a theoretical, which you can anticipate to get before the reaction actually takes place. We do these theoretical calculations with stoichiometry. That's what we've been talking about in topic 9, stoichiometry. So we can theoretically figure out what we're going to get. But sometimes in lab we don't get what we calculate, and so what we actually get is our percent yield. Things don't always work out as planned, and when we're doing a chemical reaction, it would be ideal to get the highest percent yield as possible, as close to 100%. But sometimes things don't react completely, or we lose chemicals in the transfer of something, whatnot. And we'll get more into that, something called equilibrium later on this year. So let's take a look at this problem here. So in a lab, a student produces 2.54 grams of 2-methylbutane when 2.86 grams were expected. What's the student's percent yield? Percent yield, well, let's just take a look at this. We have to first analyze what is it that is theoretical and what did they actually get. So what's given in here? What we actually got is what we get in labs. So when we do labs, what you actually mass out, what you actually solve for, will be the actual value. This is what you hands-on, what really happened. But theoretically, something we could do with stoichiometry, if we have an equation, a balanced equation, we could theoretically determine what we would expect to get before the lab even starts. So this number here often comes from our theoretical calculations, which would be a stoichiometric problem. So stoichiometrically, let's just say that we said we should get 2.86 grams, but in lab we actually got 2.54 grams. So what is our percent yield? Well, percent yield is solved like any other percents that we do. Just think of it like a test. If you're taking a test or a quiz and you want to know what your percent on the test was, you take what you actually got on the test, you take your value that you actually got, and you divide it by your theoretical value, which you could have got, the potential whole points. So you take what you got in the class versus what you could have got. So in this situation here, we take what we got in lab and divide it by what we expected to get, what we theoretically should have got. So for percent yield, let's just plug those values in. We'll put in our actual value is 2.54 and our expected value was 2.86. We take those two, divide them by each other, and multiply by 100, and that would be our percent yield.
Yes.
There she goes. Very supportive, thank you. And we have an 88.8% yield with these numbers. Okay. What will happen in stoichiometry problems? Sometimes it'll just be like in lesson 9.2, the last lesson we did. All that you do something and you come up with a theoretical value like this, and then they might say, but the scientist got this number. What's their percent yield? So it's just one more step at the end of a question that would look something like this. Now I want to talk about limiting reactants. That's kind of the main point of lesson 3. In topic 9. Limiting reactants are a more realistic situation here. So real-life ratios are rarely the same, but reactions proceed anyways. And what I mean by that is, if we had a candle, we light a candle, will it just burn forever? We all know it won't. Eventually it'll stop burning because the wax, the fuel disappears, the wick, the wax. Once that disappears, the reaction's over. But we also know that if we took a candle and we put a container over it, eventually it would burn out, but there was still fuel left over. Because why? Because if we put a container over it, it burns up all the oxygen in the container and the reaction stops. So a combustion reaction involves some sort of fuel. In this question, the fuel is propane. This is the this is a gas that we see a lot in tanks, like heating lamps or propane barbecues, things like that. In my lab, our Bunsen burners are fueled by propane. So whatever the fuel is, whether it's propane or butane or methane, octane, doesn't matter, the wax in a candle, all things that are combusting react with oxygen, and they produce carbon dioxide and water. So the fuel can vary, but the reaction stays the same. So we know that if the oxygen runs out, it will stop burning, or if the fuel runs out, it'll stop burning. So reactions go until one of these reactants runs out, and then the reaction will stop. Now with real life situations, it's very unlikely that the candle burns out at exactly the same time that all the oxygen burns out. It's very rare, very, very rare to expect that both reactants completely run out at the same exact time. So when we do this limiting reactant, what we're trying to figure out is which one runs out first, because whichever one runs out first will determine how much product you produce. So if propane runs out, then the reaction stops, and the amount of carbon dioxide and water is determined by how much propane was burnt. If the oxygen runs out, then how much carbon dioxide and water was determined by how much oxygen there was that ran out, because we still have some fuel left over. So the first step we do in limiting reactant problems is figure out how much or which one will run out first. So in this situation here, we've got 1.5 moles of propane reacting with 22.4 moles of oxygen. And we're going to burn this until something runs out. This is an especially designed vessel where there is it's a closed system basically. We have no additional gases coming in and nothing leaving. The question is, what's left over once this reaction runs to completion? So there's a lot of work to this, and there's a lot of answers in this one as well. So here's the question still. The first thing is, what is our limiting reactant, what is also in excess? So I'm going to convert propane into oxygen, so 1.5 moles of propane, and figure out how much oxygen would it take for 1.5 moles of propane to be used up. And we'll compare that with how much we actually have. You could also just as easily converted 22.4 moles of oxygen into propane and see how much propane that would use. Just do one or the other. It doesn't matter which one you pick. But I'm going to go from propane to oxygen in this example here. So I've got 1.5 moles of propane, and I want to know how much oxygen 1.5 moles of propane would actually use. And I see that it is a 1:5 ratio, and I set this ratio up for every 1 mole of propane, there's 5 moles of oxygen, and I set it up so that my moles of propane can cancel out, and then I will have it in moles. Okay, Austin Powers. And then we will figure out how much propane oxygen we have. So we convert 1.5 moles of propane into oxygen, and we get 7.5 moles of oxygen. So this means, and this is the part where you're going to have to stop, pause a little bit, and think, and evaluate what's going on here. This is saying that for 1.5 moles of propane, it requires 7.5 moles of oxygen. Now, if we look over here, we see that it needs 7.5 moles of oxygen. Do we have 7.5 moles of oxygen available to us? And the answer is yes. We have more than 7.5 moles of oxygen. Therefore, the propane will completely run out. The propane will completely run out because we have enough oxygen left over. Okay, so therefore, propane is our limiting reactant. The propane will be used up before the oxygen will. So the amount of carbon dioxide and water that's produced is based upon the propane's, the amount of propane, not the amount of oxygen. So that means that that there is excess oxygen and propane is the limiting reactant. That's what we figured out right here. So in our vessel, the question's saying, you know what? What's left in the vessel after this reaction? Well, the propane is going to be completely used up, but we have some leftover oxygen. We only use 7.5 moles of oxygen. We have more, so we had 22.4, but we used 7.5. So how much oxygen is going to be left over in here? We're going to subtract those two values. So as soon as you figure out which reactants are in excess and which ones are limiting, then you can take the one that's in excess and subtract how much you have left over. Like, yes. So 14.9 moles of oxygen would be left over. So now we know how much oxygen we have left over, and we know that there's no propane left over. So we're going to use the amount of propane that was used to figure out how much carbon dioxide in water would be used or produced in this reaction. So we already figured out that all the propane will be used, and that 14.9 moles of oxygen will be left over. Let's now convert propane, because we know propane's our limiting reactant. It's very important that you use your limiting reactant in this step. Let's convert propane into carbon dioxide and see how much carbon dioxide is produced. We're going to be basing this off of the 1.5 moles of propane that was used. So 1.5 moles of propane that was used, how much carbon dioxide will be produced? Well, it is a 1:3 ratio. So it's a 1:3 ratio. So therefore, I can convert into moles of carbon dioxide. The propane cancels.
Yes.
And we have 4.5 moles of carbon dioxide being produced. 4.5 moles of carbon dioxide being produced. The question wants to know everything though, so we got to do one more thing. How much water is going to be produced? We do the same situation. Let's convert propane to water. We start with 1.5 moles of propane because that was our limiting reactant. All of this burning determines how much we produce of everything. So 1.5 moles of propane is being used, and the ratio between propane and water in this case is a 1:4 ratio. So we convert propane into water, and we multiply 1.5 by 4, and we get 6.0 moles of water. So this is a limiting reactant question. So the question is, what's left over in the vessel? Well, we know we have no propane. It was completely used up. We have, with significant figures, we have 15 moles of oxygen. I used two significant figures since there was two in the problem. I've got 4.5 moles of carbon dioxide, and I've got 6 moles of water. So this would be my answer of what's left over in the vessel. So there's a lot of answers to this question because there's a potential of 4 different things that we have to account for these questions here. So here's some practice, and I'm giving you an equation here that is not balanced yet, so we'll do some practicing balancing here. And this one here is butane instead of propane, but it's the same thing. It's a combustion reaction. So when butane is combusting, it produces, it burns with oxygen, produces carbon dioxide and water. You got to balance that first. And the first question is just like I modeled for you. It's just like that. It's just we're using propane or butane instead of propane. So I'm giving you an amount of butane and I'm giving you an amount of oxygen. Once you balance this equation, figure out which one is in excess. Is it the butane or the oxygen? And then determine the one that is in excess, subtract what's used by the limiting reactant, and the limiting reactant will tell you how much of carbon dioxide and water there'll be. So review the steps that we just modeled and see if you can figure out how to do number 1, doing those steps. Number 2 is going to be more challenging in that the math is actually a little bit easier in number 2 as a hint, but do you understand what's going on here? Because science is not just it's not a math class, it's a science class. We deal with science problems, and here's the problem here. Do you understand how to put this together? And what I'm saying here in this one is we have 16 moles of oxygen in this question. And we produced 7.3 moles of carbon dioxide. Can you determine how much oxygen is left over? So in this one, you have a product. You're going to have to kind of figure out a little bit about what you started with. So my hint to you is convert moles of carbon dioxide stoichiometrically into moles of oxygen, and then subtract that from this value here. The final one, number 3, is a big problem. It's just like number 1 and what I modeled for you, except I'm telling you these values in grams and not moles, because that's more realistic. We mass things in grams. We're not massing things in moles, or we're not measuring things in moles right off the bat. So these things are in grams, but remember, a balanced equation is a mole to mole ratio. So for number 3, as a hint, you're going to have a lot of work here, a lot of steps, because you have to convert the grams into moles and then do what we've been doing, and then convert those moles back into grams and compare. So to figure out the limiting reactant between oxygen and butane, you're going to have to convert one of them into the other. So I would convert maybe 3.4 grams of oxygen into moles of oxygen, which then converts moles of oxygen into moles of butane, and then convert moles of butane into grams of butane mass. So there's a lot of work there, but you're going to say basically if I burn 3.4 grams of oxygen, how many grams of butane do I need? And figure out, do you have enough or not? So there's just more steps here because you have that gram mole relationship. And if you need practice with converting grams to moles and moles to grams, go back to topic 8. Topic 8 is where we talked about that. So, there's one last thing in number 3. Don't forget to answer if, once you figure out what the limiting reactant is, you'll figure out how much carbon dioxide was produced. Once you know how much carbon dioxide is produced, you can then, that's your theoretical value, then compare it with the 2.5 grams of carbon dioxide that we did in lab. So then you're going to figure out your percent yield. So there's a lot to do on number 3. Number 3 is your goal. You want to be able to answer questions like number 3, and all the other questions will be a lot easier because number 3 is going to make you do so much work. And there'll be questions like number 3 on any limiting reactant stoichiometric test you take. So this is the goal that you really want to be able to get to, is being able to answer questions like number 3. I will go over these with you next time I see you, and good luck. Save any questions you have to be addressed and we can talk about that. Good luck, and I will talk to you soon.